So yeah, I think that's my understanding of the difference between object detection and classification.
Mhm.
Is that correct?
Yeah. So this is how it would differ, right? So oftentimes classification is you have kind of like a set of different kind of objects that must be on a picture, right? So any of them kind of like must be on a picture. It's a bit more difficult when you also have a class for there is none of the objects are actually on the picture. But in this case, it's not only about finding an object, so not only about classifying that, okay, there is something on an object, which is what kind of like ResNet and typical convolutional neural networks would be used for, but we're also mixing it together with, okay, where exactly is this on the picture? And do we have more than one object? Right? So
Yeah.
the kind of like bounding box would be the object detection models. Now, they mention here very extensively RCNN and other models. SSD falls into that category as well, although they don't mention it. But essentially, we would apply, they mention kind of like sliding window. So we would still take classification kind of like neural networks like ResNet or any other similar ones, but we would simply apply them patch by patch, right? And if we have enough of kind of like confidence, so if the confidence surpasses a threshold, then that particular patch that we have just analyzed will be created with a bounding box, right? So the way that kind of like typical classification models, the ones before YOLO would work is they apply it here, right? So here, then kind of go here, then go here, and we apply the entire ResNet over the entire kind of picture. And when it detects that, okay, in this frame, there is very, very high probability, and the highest probability out of a bounding box that could be drawn like this, out of the box that could be drawn like this, and out of a box that could be drawn like this, right? Then this is how we would draw bounding boxes. Now, they take a much different approach.
So can I ask a quick question real quick? So first of all, I don't think we can see your mouse, by the way. So
okay.
But so you have this window which is scanning over the you have this window which is scanning over the image, and it's running the model multiple times, and these other strategies. Does the bounding box end up usually being wonky? Right, because there'd be like some sort of like dithering almost effect where it's like the scan doesn't perfectly line up with the object. So like, do these models have to run a few more times to optimize the position and size of the bounding box?
So, well, yes and no. So, they use, in order to optimize, so at training time, when you're optimizing kind of where the model predicted, and you kind of try to punish where the model mispredicted, right? That metric is what we call IOU. And they use IOU here as well, right? So intersection over union.
Yeah. So they use that to make... So I'm talking about the other models, the models before YOLO, the models where you have to apply a window. So they use IOU to optimize the predictions so that the bounding boxes have a tendency to be better? Or wait, or do they use IOU as a post-processing step in those other strategies?
No. So IOU is only for training. I think you mean non-max suppression. Right, so oftentimes the model would actually generate this is like, I can only speak from SSD, but I know the architectures are a bit similar in the way that they work. But with SSD, for example, it would actually generate like almost 100, well, maybe not 100, but like multiple. By the way, can you see my mouse now?
I don't think maybe it's just me.
Yeah, I can see it. It's on the screen. It's on the screen.
Oh, interesting. I can't, but that's okay.
Okay. But when you would have wait, actually, can I do quickly this? You can still see my screen, right?
Yes. Are you pulling up like a little annotation software?
Yeah,
or
yeah,
something?
yeah.
Gotcha.
I'm just drawing. Yeah. So
I actually can't see that either. Can anyone else see that? Anyway, I don't want to distract you.
I can see his mouse cursor move. I didn't see if he drew anything.
Wait. So if I change the screen,
Oh, you're using black. Your drawing is black.
Okay. Where is the option to draw in a different color? Okay, but can you see that I'm trying? Like, can you see the picture?
I can see your screen. Yeah, it's like the figure 5. Oh, actually, I think I see your mouse now. Is your mouse a?
Try the button beside it for the color. Oh, there we go. The color. It's the button beside it with the black rectangle. I think that'll change your color better. I think
that's
this one.
Oh, okay. Shoot! Yeah. Wait, hold on. It's a network problem. My bad. Sorry to interrupt you.
Okay. So you can see the screen, right?
Yeah, I might have to join, leave and come back because, well, sorry. I'm so sorry. So I live in a bus, and my internet is cellular, and it's been stormy lately. I'm gonna leave and come back really briefly.
Okay. Yep.
Hello, I'm here, and I think I see your screen, and I think I see a little box in the middle, and I see your cursor, so we're all good.
Okay. That is good.
Sorry.
No, it's fine. So, if we were to apply it, yeah. So your question, right?
Yep.
So usually it would kind of create multiple bounding boxes because the threshold for multiple bounding boxes around kind of like the place.
Mm-hmm.
Would be, why does it fill? Okay, well.
Yeah, it's that middle. The middle one is your fill.
Nope.
Where you see it's red, the red solid box. That's your fill. No, the one beside it.
Oh, okay. So no one. All right. So it'll create multiple kind of bounding boxes, right? So also bounding box like this, because all of them would have kind of very high IOU, and oftentimes the way that you choose the one at prediction time, the one to actually display, would be so you would eliminate the boxes that have too high of an IOU and choose the one that has the highest probability of image being there, right? So the one that has the highest sort of confidence, although in this paper confidence is defined as a bit of a different thing, right? But if the classification model says that this is a person with higher probability for this large kind of this actually picture is going to be better because it would create also a lot of kind of bounding boxes like this.
Gotcha.
Right? And it would be very difficult to, so you would probably get this bounding box with the highest probability for being a bird, and this bounding box also with the highest probability, right? Now, how do you eliminate boxes that are, let's say, in the middle? Because that would probably yield quite a high probability of there being a bird as well. And you would eliminate it with IOU, so this metric, being very high with the other bounding boxes.
So would you likely end up with one bounding box instead of two? In other strategies, not in this one.
No, not really, right? The goal there is to have so IOU is, so the non-max suppression is responsible for eliminating the bounding boxes that are like multiple bounding boxes that describe essentially the same object, right? So the goal there is, would you get more objects potentially? I'm not sure. I don't know what the probability would be.
So
yeah.
I don't want to distract. So like my understanding is, so you have this red box, and let's say like, so we're talking about other strategies before YOLO. These ones that scan through and do a prediction for the entire model for every sub window. So my understanding is you have this little square this red square, and it would scan from left to right, top to bottom, and you would then get essentially a matrix of probabilities for every window, right? So every window now gets assigned, this is likely to contain a bird, right? So now essentially what you have is a series of overlapping windows that are likely to contain a bird. So my thought is you kind of would group these windows together. That's my assumption. Before YOLO, you would like, if there are a series of windows that are contiguous with one another, that are connected, you would group them into one bird. So I would assume, based on my very naive assumption, I don't understand these models, I don't think, as well as you do, but I would assume that if you gave one of those older models that picture of two birds, you would get a box that is highly likely to be bird, and as a result, you would get one window that contains bird instead of two separate windows containing birds. That was my assumption.
How I understood it is that the other approaches would detect the two birds, but they're much slower because of how they're implemented, while YOLO is supposed to do it faster. That's how I understood it.
If anything, the previous approaches would somewhat be better. At least the paper mentions that, especially when it comes to a lot of small objects that are overlapping, like very tiny objects.
It did mention that.
Then,
I think the paper mentioned that.
The previous ones would be better, right? And this is where also they mention like the combination of RCNN and YOLO. Again, I can send you kind of like the link to how they eliminate the bounding boxes, because it's called non-max suppression, and they even mention in YOLO that they also apply non-maximum suppression, but I believe it might be a bit different non-maximum suppression or the same. They did not mention anything about it, so maybe it's the exact same one as they use. But anyway.
So I'm wrong, and I'm wrong, and if I want to learn better, I should probably look at that other link.
I can send you just kind of like a small chapter from a book that perfectly describes IOU, and like, have you read up on IOU?
No, I researched IOU for the purposes of this paper, but not in depth and for a variety of models and a variety of applications. I did see one brief one that was talking from like a metallurgistic perspective of individual pixel classification. What is it? Semantic classification, I think is what it's called. Semantic segregation. When you like classify individual pixels. I saw IOU in that context, but I still need to learn a little more. So, okay, I don't want to, sorry, I don't want my question to eat up like all of the time.
So what were we on? Hold on. I lost that train of thought. It's this. Oh yeah, I was meaning to say it's the exact same IOU, right? They do not mention it as a different, and this is a general kind of like more of a, I don't know, statistic. It's kind of like a weight, but for object detection. It's a standard metric that they also use here. So if you read up on IOU, the previous models use the same one, right? There isn't big of a difference. Right. Now, okay. The annoying part is that, can I do it this way? Okay, because if I do done, do I still have this picture? Will I be able to draw on it? Does anyone know how to? Okay, there should be a drawing. All right, let's go back to the paper. So the next thing, so what they propose is that they essentially use regression, or more like simply a fully connected layer, so kind of multiple regressions, to decide on kind of the objects, right? So they don't apply classification multiple times. They apply the convolutional neural net, like the convolutional layer, only once at the very beginning, and up to the final connected layer. This is the exact same structure as you might see in a typical convolutional neural network, or a ResNet, or any of these.
Mm-hmm.
But the difference is in the fully connected layer, right? So up until here, it goes just as normal. And then it's simply I assume it's just a normal convolutional, fully connected layer that then transforms the outputs yet again into, in this case, a three-dimensional output. Only kind of, yeah.
And the dimensions of that output are S by S by...
Yeah. By B multiplied by 5 plus C.
Yeah. Yeah, which we were talking about. Yeah.
Yeah. So I guess I'll talk about this a bit more in a second, because I was considering why that specifically is. Now,
yeah, especially the 5 as well. I'm curious about why the bounding boxes needs to be scaled by 5 as well.
Yeah. So the 5, to answer a quick question, comes from X, Y, WH, and the confidence score.
Yeah.
Yeah. So this is where the 5 appears. Okay. So let's come back a bit. Now, this is something that I kind of struggle with understanding. What do they mean by separating bounding boxes and confidence predictions with kind of class probabilities, and where does the S by S grid come in? So essentially, and they don't make a good kind of explanation here, but there's a difference between how they train it and how they predict based on the model, right? So, okay, so now let's kind of explain the kind of functioning of it. Should I start with the training or the prediction?
That's up to you.
Okay. So let's start with the training, right? So in the training, essentially, wherever the object is, right, they divide the final, and here's the kind of important note. They say the picture, they don't actually divide the picture. They essentially divide the final feature map, right? So this part right here, and it is explained pretty well, right? So when you apply a kind of convolution, right, it decreases the image, right? Now let's assume you don't have padding and a stride of 1. Then that would increase by 1 in every dimension. I don't remember the math, but you get the idea, right? So that means that now every single value here, right, this little tiny speck will be a bigger kind of patch on the picture, right?
Mm-hmm.
Right. So the feature maps, the values of feature maps, every consecutive feature map essentially corresponds to a bigger and bigger patch, right? Because you're kind of downscaling the information, right?
Yeah.
Yeah. So this kind of final feature map will correspond to this S grid, right? So this is what the final kind of feature map is. right? There is a great
Isn't this similar as well to the intuition behind pooling layers to reduce computational complexity?
So the pooling layers would be part of it, right? But pooling layers would pooling layers kind of complicate the this a bit, because now you're downsampling kind of the information even more. So you're losing a bit of information, right, when you're decreasing the feature map. But you still can kind of view it as a part of a great book, by the way. And I'm looking for like a cool picture, or actually, I have it here, where they explain this is segmentation.
So while you're looking, if I can,
Where is it?
Yeah. So my understanding is, for the purposes of the paper and describing it from a really high level, they draw this S by S grid, which is a useful idea. It conveys the idea, but it is a little misleading, because it kind of implies that separation happens on the image level, right? You segregate the image into these different groups, and then you analyze the groups, and then you build bounding boxes, whatever. That's all well and good and fine and dandy in terms of like a really high level, but actually the way it ends up shaking out is the division into grids happens at the end, after featurization, not before featurization. And to me, that's actually, I didn't really realize that I didn't understand that until now. But that's really crucial, because the whole idea of a convolution is you're aggregating sort of general ideas. So you're like, because you're basically, your S grid then has information about its neighboring grids to some extent, because your convolutions bleed over to those other grids. So it's really, really useful to do that separation after, not before.
They would bleed over. So kind of like
maybe the understanding would bleed over, not necessarily the anyway.
So what I know what you mean, but if you were kind of like downsampling, right? So on feature layers, the entire feature map would be corresponding to the entire picture, right? But an individual kind of pixel would be corresponding to information only about this tiny patch.
Yeah, I guess so.
Yeah.
Yeah, so there maybe, it's a new concept to me, but like, yeah.
Yeah. So at training time, what they do is, and here's what I kind of found tricky, right? But essentially, for the final kind of feature map, right, they take values from this. So yeah, in this case, they divided it 7 by 7. Yeah, so let's go 7 by 7 example, right? So they take the grid. Now, how do they define? Because here's an issue, right? You have no assurance that the object is actually going to fall inside or outside, or it's going to spill into multiple of these, right? So essentially, and this is what I kind of didn't get at the first read either, but the prediction, of these values, right? X, Y, W, H is meant to predict how, depending from this grid, so in relation to this grid, it's already meant to sort of predict that the object is bigger than just that simple grid. Which is kind of weird to understand. But yeah, I read up on it, and these coordinates, right, when it's predicting the coordinates, it's predicting already the coordinates for the entire object, right? So in this case, you can see that the bounding boxes are in these weird places, and they're not corresponding to the S by S grid, right? It might be a bit confusing, let's say, with the dog, because it kind of overlaps here, but it's not predicted. It's predicted essentially by just one of these grids, kind of in essence.
Is the center in the S by S grid? Like,
yeah. So you're taking, and this. So now we are talking about the prediction time, right? You punish the network. You take the middle grid of the object. So you define it as the middle grid, and you've got two statistics. So you've got the confidence, right, will be probability of the object, and you set the probability of the object as 1 if this is the central grid of a given object, 0 for everything else. Right? So for a bike, this will be the middle grid, and the probability of this will be 1. These ones will have probability of 0. All of these, right? Right, and then for dog, this one would be 1, or this one, it's kind of difficult, yeah, will be 1, and this is kind of indicated, they pictured with a loss, right? So this one will be x coordinates, right? And here is the width and height of the picture, and this one is this one indicates that the probability of an object is set to either be 1 or a 0, right? So we punish the classificator. Essentially, we kind of train it to predict only from that one simple grid, and sort of extrapolate about the remaining picture. Now, here is kind of also a very tricky part, because this is kind of fully connected layer. Then, although in this case, right, a single value will be corresponding to this S grid, right? So to these patches, like we just said, and it will be corresponding to just 1. Because of the fully kind of connected layer, the patch, so this patch in essence, will also contain partly information about the entire picture.
Can you repeat
is kind
that?
Of confusing. Yeah.
That like last sentence. Can you repeat that?
Yeah. So because this is a fully connected layer, right? And we create here the output 7 by 7 by 30.
Mm-hmm.
Each one of these kind of tiny values, right? So you can imagine, or you can imagine just a kind of a row across the third dimension, right? So a single, like 1 by 1, or like, let's say, I don't know, 1 by 1 by 30, right? So this row, because this row will technically be corresponding to the first and 1024, but because there is a fully connected layer, it also contains information about the remaining part of the picture.
Oh, and that's because I was wondering, I was like, so you're asking it to predict the middle of a bike? Like, not only are you asking it to know that there's a bike in the thing, you're penalizing it for not understanding that it's in the middle of the bike. So how could it possibly, if it's looking at individual components of an image, understand where the middle of the bike is? But it understands that by comparing the different segments and then reasoning about which one of them is the middle.
Yeah. So
that's
in essence,
so cool and fascinating. It makes so much sense, and I didn't know that before this. That's so freaking cool. Anyway.
Yeah, I same as you, Dan. I thought there was that image level as well. When the foundational difference that it's done in the middle, while not knowing what the whole picture looks like, but this information I got from the other gradients, right, on where yeah.
Yeah. So this is kind of in the loss function, right? Now, so you would take, so this is at the training time, right? But because of the convolutional, because of the fully connected layer, right? At training time, you only pick which which kind of column and row has a confidence scores higher than your given threshold, and the ones that have, then they must have objects, and then only then from the kind of like confidence scores, you pick these values. But these values again are not constrained to just the tiny kind of grid, right?
They they are constrained to having an origin within. Like the width and height can extend outside, but the X and Y are within the S, right?
Yes.
So there is that constraint, which is an important point to the idea that you only are selecting one grid and that is the central grid. You're only selecting one S by S square.
Yeah.
Cool.
Yeah, and the interesting also thing is that they are teaching it to predict. So at training time, right? In essence, they because this is kind of what I didn't get, right? And on one hand, they're trying to kind of predict the probability of the object and the IOU. And this is where this comes in, right? Because it's for every bounding box, there's confidence and the 4 coordinates. And I remember not really understanding because here they say C for C classes, right? Now, where's the probability of the object, right? Where does this fit in? And actually, at training time, and this is an important distinguishment, at training time, they kind of pass the values of these two that they wanted to be, right? So they calculate manually for that given guessed kind of bounding box what will be the IOE with the true prediction, right? And the probability of the object is simply 1 or a 0. But given that this is a regression, the network can actually predict something in the middle, right? So in a loss function, this will be exactly, I believe, this one. Yeah, the probabilities. The true probabilities, right, will always be, and we punish this only. Sorry, we don't. Not that we punish it, but we only do this. And give me a second. I will just mute. Yep. We only do this at training time. This will be. We set this as 0 or 1. Right, but the probability will often be, let's say, I don't know, something in the middle, right? Sometimes the kind of, okay, that one I believe this is because the C1 is for classes, correct?
I think so. Right. I think that's the I can't remember off the top of my head, but if you scroll up, it defines what C is. So if you scroll up kind of to where that image was, scroll up a little more.
Yeah, I believe so. Yeah.
So it goes through A. So there's each grid cell predicts B, and then if you scroll down, I think then it defines C. Yeah, each grid cell also predicts C, conditional class probabilities. So I think C is the probability of a specific class. So it's a vector based on all the classes that you have. So there's
sorry.
Sorry, you mean the smaller C.
So C is actually, so in this case, it's a probability of the object. And you can see that this is C in classes.
Yeah.
Right? Okay, so this one is quite confusing. Okay, so in this case, so C, in this one, the C will be the confidence score. And, and I believe, okay, yeah, so, sorry.
Predicted confidence score was C hat, right?
sorry. So to go back, so the probability of the object. So you punish those separately at training time, but they become kind of one value at test time. I know this is a bit kind of like weird, right? But the IOU is defined by coordinates. So this is how we punish IOU, right? And this is how we punish kind of the probability of objects. And also, in this case, that there is no object, right? And this is just the probabilities of classes. So this is most likely just a vector of 0, 0, 0, 1, 0, 0 for which class is in the object. And this one, right? So now let's go to, does everyone kind of understand, I guess, this part, right? So confidence and bounding boxes.
Do you want to go over it one more time super briefly?
Yeah. So the confidence, right, at training time, right, they separate this as the project probability of the object. And
It's, so to be specific, it's I understood it as not the object, but an object.
Yeah, of there being an object.
Yeah.
I believe.
Like any object of any of the classes that are defined.
Yes.
Yeah.
Right. So this is what they meant by the. This is what they mean by probability of an object, right? And they set it to 1, right, if it's in the center, and 0 for everything else, right?
Mm-hmm.
So only this grid, and this grid will get probability of 1. Everything else here has 0.
Yeah.
Right. And this is kind of how they train it. Now, this was kind of what I found a bit confusing as well, but they calculate the oh no, they only calculate, because there's a leading one, so they also only calculate the IOU for only the cells that have the object as a center, right? So then that particular cell will have its gradient adjusted to fit the object better, right? So to be kind of bigger in this case, right? So let's say that the first prediction was a bit smaller, and it will be adjusted to have a higher prediction. We don't care about any of these tiny boxes, right? We don't punish the gradients kind of the remaining sort of parts, right? So this is where this is kind of interesting, because they take like here is the 1, right, and it's a 0 if there is no object, right? So it's both for.
Oh, gotcha. Yeah. So it's like it's basically, it's only computing gradients on the S squares that have an object within them, because otherwise the value is 0, so there is no gradient in the other boxes.
Although they punish the confidence,
that which makes sense, like the the confidence that it is a dog or a cat or a because it should, those squares should correctly identify that it is a dog. But you don't care about the bounding boxes because they are not the central dog square.
Yes.
Cool. So you're training all of the squares to recognize.
No. But the probability, right? You're punishing the probability for there being an object. So the confidence value, you still only punish as there being an object for the central one, right? Mm-hmm. But all of the other squares, you punish the confidence to suppress it to 0, possibly, right?
Oh, okay.
But you don't adjust the gradients of bounding boxes for places that there is no object.
Gotcha. So right? What notation specifically defines that distinction between the two? Like,
it's the 1. Oh.
Yeah, whenever you zoom in and you try to highlight it, it freaks out, by the way. So if you try to highlight again, it'll So
Yep, okay.
this
No
sort of
highlighting, but
one OBJ
the leading
IJ.
one. Yeah.
Uh,
So they say one denotes if an object appears in a cell I and that bounding box, right? So IJ is for the bounding boxes, and yep.
Oh, so there's OBJ and no OBJ, and that defines what you were mentioning.
Yeah.
Gotcha. I didn't
So
honestly.
this is,
I kind of ran out of time, so I kind of stopped reading super closely around here.
Fair. So this is why, because I believe this is so kind of convoluted kind of equation, because they're summing over all of them. Because in this case, in object detection, right, you naturally can have multiple bounding boxes, right, and multiple objects, right. This is the key problem of object detection as opposed to classification. So you might have like 20 objects, right? In which case, the bounding boxes for 20 different kind of squid grids will be punished. But let's say if you only have one object, then you only learn so you only adjust the gradient in respect to one grid.
Yeah.
And so now the kind of prediction, kind of once you get this, becomes quite easier because you pick. So you go over, right? So this 30, right, will be B multiplied by 5 predictions. So the confidence, right? So you would kind of slice this part by the confidence, right? You would pick the ones that have confidence higher than the threshold, right? Ignore everything else. And then from this kind of confidence, from the values that have high confidence, you would take the respective X, Y, W, H. This is how you draw the box, right?
Mm-hmm.
And from this same prediction, right? So let's say that this is a point that's, I don't know, second. Well, okay, in this picture, it would be grid cell 1, 1, 2, 3, 4, 5 by 2, right? So you go 5 and 2, right? So this little, oh my God. So you choose this point and on this tensor, you find the confidence, right? And then in that row and column across this, you pick these ones, right? Which can extend outside. And then you pick this cell and you get the highest classification probability.
Gotcha. So, so before in the beginning we mentioned that it's actually worse at detecting a lot of tiny objects, and that's probably why, right? Because if your tiny objects are within that S thing, then it's hard for it to, there's like an implicit resolution to the size of objects based on this concept of an S by S grid.
Yeah. I can imagine, and I think you can even, like, if we really zoom in, right? You can even see here that there isn't a lot of kind of predictions for bounding boxes inside. Like, there isn't more than one bounding box prediction for entire grid cell. And this is what I think they mean when they said, this is, I think, the reason why it struggles to find like multiple small objects, because if there will be 2 tiny objects inside this tiny grid cell, then naturally the confidence will be very high, right? And the class probability will probably be correct. But because there is only one grid cell, right? There's only one prediction for that grid cell. There is only going to be one bounding box, right? And that bounding box could be correct, but it's just one box.
Yeah. So also, I think somewhere it mentioned this idea that certain grids will become, or certain bounding boxes will become specialized to certain classes. Did you notice that? I'll extend this.
No.
I don't know. I might have been reading something else, but I heard this idea that like because you have multiple classes and you're generating multiple bounding boxes, what ends up happening is certain bounding boxes start getting good based on their width and height at detecting certain objects. Um, based on like you can think of like
This
there's
would probably be a good description because yeah. So what you're describing, I assume, right, is that the confidence gets it right, right? So that the first part gets it right, but then the grid cell fails at describing what class it is, right?
yeah. Well, so more so I'm like oh man, I wish I knew where this was. I thought I read it in this paper, but I must not have. I must have read it somewhere else. But basically you know, an airplane has a certain general shape, and a boat has a certain general shape, and a person has a certain general shape. So each of these S by S grids has an arbitrary number of boxes that it creates, right? And that's how you get this massive thing of boxes. And each of those boxes,
they set them usually manually, but yes.
yeah, it's like a hyperparameter, like the number of boxes, the number of bounding boxes
Per.
that can be generated. So what I read was that, you know, each of these bounding boxes is kind of static, right? Like there's bounding box 1 through n within S, and what I read ends up happening is bounding boxes 1 through 3 end up being sort of specialized for dogs. Bounding boxes 3 through 9 end up being specialized for airplanes. And this has a lot to do with the width and height, because the aspect ratio of different objects has a tendency to maintain some level of consistency from object to object. Like dogs are generally either upright or horizontal. Bikes are generally square. Airplanes are generally short and wide because they're flying and they're far away. Stuff like that, which I don't know if that's correct. I feel like maybe I'm just making that up, but I remember I remember reading that.
If you I don't know, again, I have not delved that much into kind of this part because it's just
I didn't either. I didn't even read that part.
Yeah. So you didn't read it in this part?
No, I didn't. Well, I skimmed through some of it, but it's kind of like famous paper syndrome. It's like they have to prove that everything's accurate. So to other researchers, they're like, look at all the experiments we did and stuff. But now that it's been like however many years and it's been cited 5 billion times, I'm like, whatever. It's really good.
Like we just assume that we're reading the paper because we know it's good.
Yeah. So I didn't even bother, like, because I have limited time, so I just.
But also about the object misclassification that you mentioned, I thought that I could be wrong, but I remember I encountered this when I was reading, I think, the Lime paper. I think it was one of the local explainability papers. A lot of computer vision mistakes also happened with respect to the context in which an object was positioned. So, for instance, here in this case, Vin Diesel, whoever is jumping here, is not only because of the shape, but also because of the sky behind.
Yeah.
And because these other contextual elements that are in coding the boundary box that will influence classify an object as such.
Totally. And I mean, like, so I guess because there's this sort of separation between bounding boxes, the bounding box is totally accurate, but it's the classification of the S grid that the bounding box is containing which is inaccurate. Which is interesting. Okay, so Bart, do you have anything else you want to mention really briefly? We only have a few minutes left.
Yep. Yeah, so wait, can you hear me?
Yeah.
Okay, that's good. So any questions, I guess, with the paper? Because I think if you have kind of mentioned, because that's quite interesting what you said, that like some bounding boxes will be specialized. If you find again where you read that, just let me know, because
Yeah, I have it. It's the line paper. I'll send it in the Discord chat.
yeah. Please do. And yeah,
Cool.
I guess that's everything about it.
Yeah, Bart, I
Yeah.
thought you did a fantastic job. You're so much better at math than me, so it's really cool. Like, because that's where the rubber meets the road, right? So I think the next paper is,
Attention is all you need. I think.
yeah, attention is all you need, which is
Yeah.
an NLP paper. I'm really weak in NLP, but I'm currently interviewing for companies that do a lot of NLP. So I'd kind of like to own that paper if I can, if everyone's okay with it. And then maybe Adam and Shane, we can get you guys in on the owning of papers. You guys can like think of papers that if you guys are okay with that. I've already owned a paper, so if anyone's really into it, then you can take it over.
Sure. Yeah, no, yeah, I think it's yeah, we great if you do attention is all you need. And yeah, I'd also recommend this 30-minute video, but from Yannick Culture, the way he really walked it, in case if because it is pretty confusing. Like, the first time I read it, I had trouble following it. But
Gotcha.
But it makes a lot of sense.
Cool. Yeah, if you can link that in Discord, that'd be sick. So sorry, I'm interrupting because it's gonna cut us off. But I'll try to own that paper, I think, if everyone's okay with it. We'll talk more in Discord, it's fine.
Sure.
And we'll meet in a week from now, same time. And also, if anyone, we're kind of following reading paths, but not really. Bart was really interested in this paper. So we kind of just went with this paper. If anyone has another,
it is still on the reading list.
yeah, it is. It's on like it's not on like the general one, but like basically the moral of the story is like we're not really strictly following any particular reading path. There is a sequence that I think a lot of people recommend because of more and more complexity. But if anyone's interested in any of the papers from any of the reading paths, I think it's cool if you're really interested. Otherwise, we can just agree on a next one, whatever. But all right, well, it's gonna kick us off at any time. I don't want to be like weirdly interrupted, and it was a pleasure seeing everyone. Adam and Shane, it's really good to meet you, and Bart, thank you so much. And we can continue the discussion out of the the chat as well. So thank you guys so much.
Thank you.
Thank you. Bye bye.